Okay, welcome everyone to this continuation of what is machine learning doing for you in mathematics. So machine learning, how can we use AI to advance mathematics? Keep in mind it's kind of a crucial question because mathematics is like the science of reasoning. So essentially this is about how good are we in reasoning. And turns out so far, at least if you go scroll back and you really want to watch the other parts of this series, you will realize that it's a bit disappointing. There's not much reasoning involved, but it's also very encouraging. And I should say that because most of math, most of the machine learning, the other way around, most of the machine learning needed for mathematics is pretty baby machine learning. Yeah. So as a mathematician, you're always used to like looking at other fields and then they just use baby mathematics. Because baby mathematics, I mean, people things people have figured out like hundreds of years ago, maybe not that much, but quite a while ago. And other fields are always way behind the modern research in mathematics. And similarly, mathematics, the machine learning part you need for mathematics is like way behind usually the machine learning research, which is kind of a fun thing to see as a mathematician. The good thing about it is that a lot of problems in mathematics, you can still attack them with very, very easy methods from machine learning. So maybe that's the right time to get started. There are two things to be said here. First of all, I'm recording in 2025. So if you're watching this in 50 years, you probably should do something different. But also, times change. And another problem already in 2025, I'm a little bit behind with the literature, so certainly more modern papers will use more modern methods. But the paper I'm following today is kind of one of the first of its kind, really, really readable paper, very nice, but from 2016. So when I'm recording this video, this paper is essentially already 10 years old, which in this field, this is like moving fast as hell, is the very, very old. But anyway, really beautiful, highly readable, and we're going to discuss that. And they really only use a very plain vanilla type neural network, and they get very impressive results. So I say that again as an encouraging word for everyone. If you want to do it yourself, I think you can actually. But now let's have a look at something more formal. Not really. I'm not going to do anything formal. It's a video after all. But anyway, this video is about prediction. Prediction is something I usually like to identify with conjecturing. So the math terminology for prediction is conjecturing, or the real world terminology for conjecturing is predicting. But I make a tiny difference. I'm curious whether I can actually spot the difference between predicting and conjecturing. So predicting, let's say, is to guess a property, well, of a graph, for example, or whatever, of something without knowing the full information. Yeah? If you think about a graph, and yeah, you could ask the question, is it Hamiltonian? So does it have a Hamiltonian circle? Very difficult to compute. So it's likely that you will never have the full information, but you can maybe make a prediction, right? So that's the whole point. You can predict, with 90% probability or something, this graph has a Hamiltonian cycle. And I also gave you a real world prediction, like house price prediction. Kind of not so difficult. You can actually do it, but of course you will only end up in a certain range, in a probability range. You can do the same in mathematics for essentially everything. So if you're a number theorist, predicting the rank of an algebra of an elliptic curve is something else that is really difficult, but it's actually doable. In this case, with a machine learning approach. So that's what I would like to call prediction, like getting information about something without knowing the full information. Right? If you have full access to information, you don't need any prediction. You know everything anyway. So that's what predicting is all about. And the type of prediction I would like to talk about, well, was this paper, Neural Network Approach to Predicting and Computing Knot Invariants. So there should be something related to knots. And here we go. So a knot is really just a piece of string, group, that you kind of put in some way or form in 3 space. So this knot here is really just the same as the unknotted one. Just a piece of string that you put in 3 space. Essentially the idea is the following. The one-dimensional object is just a line, right? The one-dimensional object is just a line. What can you do with a line? Not much. It's one-dimensional, but you can twist it, tangle it, and knot it. And that's where knot theory comes from. And this is like why not theory. It's kind of the first non-trivial operation you can do on an almost trivial space, but on a non-trivial space, on a one-dimensional space, is you can knot it. Yeah. There you go. And then knot theory plays a crucial role in all of low-dimensional topology. Now, knots are like really everywhere, and people just love them in general because, I don't know, people love knots. They build those tables here and out of kind of real string type of knots. But you can already see lack of the difficulty here. So usually knots come in this funny fashion. I'll show you some more pictures as we go along. And you want to know which knot it is, right? So this is the unknot. It's kind of easy to see. But if it's getting really tangled, you might not actually easily see what the unknot is. And then knots like graphs have many properties. The minimal number of crossings you need to draw it. The genus of a knot. The unknotting number. So the minimal number of crossing changes you need to do until it gets unknotted. And as for graphs, usually these are like really, really difficult to compute. So a lot of knot invariants are absolutely not trivial to access. And this is where our neural network approach comes into the game. Wouldn't it be great if you can just you just draw the knot on a piece of paper, take a picture with your phone, neural network scans it and tells you, by the way, the genus of this knot is 15 or something. Or the number of crossings is 12, something like that. Yeah? Wouldn't that be great? The paper I discussed does something different. It doesn't scan knots, so it's not using pictures, but like break presentations. But anyway, it's kind of the dream you have. And then you realize, I will make this picture a little bit bigger, so because it's like really, really nice. Then you realize, so these are 10-fold knottiness. So a list of knots with 10 crossings, and they get pretty insane, as you can see. Ooh, really, really kind of difficult. And why are they not the same? I have no idea. But someone spent a lot of time doing this. Yeah. So link to all of the pictures are in the description. Of course, it's not my picture. So people spend a lot of time trying to list knots, and there are just many of them, and it's like really difficult to distinguish them. And they have very, very different properties. So knot properties. So there are many, many knots. The number of knots grows exponentially in the number of crossings. So for 10 crossings, you already have quite a few. And then it essentially takes times 6, roughly, with every number of crossings. For 11, you would have 6 times as many. And for 12, you would have 6 times 6 as many. Quite a lot. And yeah, so the knot properties, they usually vary drastically. It's not a continuous but they just jump randomly, essentially. So predicting them is kind of key. And to convince you, well, you might say knot theory, boring. Nobody cares about knot theory. So why would I care? But turns out, this is one of the things where real world is actually not far behind mathematics, if you want. So all of a one-dimensional structure, like a DNA, or a protein, which is really just a chain of molecules. Yeah. What can you do with it? Oh, it's a one-dimensional thing. What can you do with it? You could knot it. And turns out that proteins and DNA, they really like to knot themselves. So here's some cool pictures. If you Google DNA knot, you can find many, many more cool pictures. Like this is beautiful. Oh, look at this. A DNA that knots itself. Here's another one. DNA knotting itself. DNA knotting itself. We already had this, and then they really would like to know. This is like a little more difficult to tell. So we really would like to know. I thought there was a nice table somewhere, so let's have a look. Nice little. Oh, this one is good. So they really want to know what knot it is or what properties it has, because the properties will determine like the chemical properties. Yeah? So the properties of the knot, the DNA or the protein forms will determine the chemical properties. So it's like a really interesting question you can ask. And this paper was one of the first of its kind, I think, and very impressive results. So with a very, very basic neural network, they got more than 90% accuracy. I can put up some more precise numbers. So so where are some more precise numbers here? Quasi-positivity detection, blah blah blah. Ooh, some really good numbers. Anyway, so more than 90%. They had a very, very basic neural network. So a completely vanilla neural network, nothing fancy. Again, you can do this yourself. It was nothing fancy, completely vanilla. They got very impressive result about completely non-trivial kind of not properties like quasi-positive and slice genus. So slice genus is a 4-dimensional thing, very difficult to compute, like highly non-trivial. The minimal genius of a surface, and I can pull up the picture that bounds, not my picture as I said, link is in the description, but this one is really good, that bounds a knot in 4 space. So here's some surface in 4 space, our little knot, it's really just a circle, and you can look for the minimal surface, the minimal genius of a surface that bounds the knot smoothly. You know, already difficult to define, it's super difficult to compute, and they had a neural network that can predict that. And this is excellent because if you just run it on knots where it's not known, it gives you a prediction, whatever the number is 5, and then you can go ahead and prove it. That's exactly what you did. That's exactly what they did. So it's like, as I said in the beginning, I would like to make a mild distinction between prediction and conjecturing, but this is like a form of conjecturing, right? You conjecture the genius of this knot, whatever the slice genius of this knot is 5, and then you go and prove it. But again, I want to draw your attention to the high level of success here and the easiness of the neural network. And there are now many, many more examples along the same line, because this was like 10 years ago, right? So the field has advanced, obviously. But it's kind of still one of my favorite papers. Very easy to read on this subject. Anyway, I hope you enjoyed this video, and I also hope to see you next time.